Hello again. In today's video, we'll be dealing with a topic frequently called kinematics in your textbooks. And this has to do with constantly accelerated motion, meaning motion in which the acceleration is constant. Because this is the case that's the simplest to deal with, so this is what we will be starting with. So what I'll do today is I'll be deriving 5 equations that will allow you to solve all of the problems dealing with constant acceleration. So let's look at the 5 variables that we'll be looking at, and I like to use the mnemonic SUVAT for this, where S is the displacement. And remember, this is a vector quantity, so direction does matter, and we'll come to how to deal with that right further down the road. And then here we have the initial velocity, which is the velocity with which the object starts off with, and then F will be my final velocity. And then of course we have acceleration and time. So at any one time we will be given 3 of these variables, and we'll need to solve for the 4th one while ignoring the 5th one. So I'll just show you what I mean when I do examples after I derive these equations. So let's go right ahead and derive the equations. So first off, I'll draw a graph to represent motion of the object. So a graph, and I'm going to have time on the x-axis and velocity on the y-axis. And because the motion is constantly accelerated, remember what the slope of the velocity time graph represents. Slope of velocity time graph represents acceleration. So I'm going to have a constant slope because the acceleration is constant. Right? So the slope is constant, and which makes it a straight line. And this will represent the motion of my object. So I'm going to have my object start at some initial velocity here, let's call it u, and end at some final velocity, we'll call it v, and that's what that point is. And then I'm gonna have the time in which it goes from u to v be just t, so that's gonna represent how long it takes for the object to go from the initial velocity u to the final velocity v. So the first equation comes when we look at how we get the acceleration. Well, the acceleration is the rate of change of velocity, which means it's going to be the slope of this graph. So I'm going to take the rise here over the run. So the rise happens to be v minus u. Right, so just that, whatever that number is, subtract that number, and the run is simply the time it takes for it to get from u to v. So that defines the acceleration. Acceleration is v minus u, the rise, over run, and frequently this equation is rearranged. So I bring time up, and I'm going to bring the u over, which makes it a positive. So I'm going to have v equals u plus at. So that's the first of my equations that I'll need. The second equation comes when we look at the area under the graph. So remember what the area represents. The area represents the displacement. Alright, so the area under the velocity time graph, we looked at that in the last video, represents displacement. So you recognize this as a trapezoid with height t, and top length u, bottom length v. So the area is my displacement, and the formula for a trapezoid is half top plus bottom times the height, right? Because if you turn this on edge, you'll see that it is indeed a trapezoid. So this is also written half the initial and final velocity summed together is the average velocity, which is written v with a bar on top frequently. So this is usually taken together to be the second equation. To derive the remaining three equations, what we'll do is we'll simply plug each of these into one another and arrive at the second equation. So the first thing I'm going to do is I'm going to plug the first equation into the second one. So I'm going to be replacing v here with u plus at from the first equation. So I'm going to have s equals half u plus, I have a v here, but instead of putting a v, I'm going to put u plus at, u plus at, and then multiply by the time. So inside I'll have two u's, and that half cancels that 2 to give me a u, and the t comes in, give me that t. I'm going to have the second term being half a t, 2 factors of t, gives me half a t squared, and this is my third equation. For the next one, I will substitute out u here. So from here, you can see that u can be written as v minus at if I bring at to the left-hand side. And instead of putting u here, I'm going to make it v minus at. So that's going to be half v minus at plus v times t. So now you see I have two factors of v, which multiplied by the half is going to give me one factor, and time comes in. And I have subtract half a time 2 factor squared from the outside coming in. So this is similar to the third equation, except that I have the initial velocity replaced with the final velocity, and the sign in the middle switched to a negative sign. And finally, to get the last equation, I'm going to rearrange this. So from here, you should be able to see that I'm going to get rid of time. So time is going to be v minus u over a. So I'm going to replace the time here with v minus u over a. So let's do that. S is half u plus v, and then v minus u over a. So I have 2 and I have a at the bottom. I'm going to bring those out here, and I'm going to switch this around and make it v plus u so that you can see clearly that this is a multiplication between the sum and a difference. And when you have multiplication between the sum and difference and you FOIL it or you expand it, you're going to get a difference of the two quantities. So v squared minus u squared. The 2a comes up and multiplies the s to give me 2as. And this is frequently written as v squared is u squared plus 2as, which is the fifth and final equation. Now, if you inspect each of these equations, you notice that there is one quantity missing from each of them. So on the first equation, time is not present. On the second equation, I don't have acceleration. On the third one, I don't have the final velocity. Fourth one has no initial velocity. And the fifth one has no time in it. Let's take a look at an example to figure out how we can use these equations. So say I have a car that's moving along. With some initial velocity. Let's say it's moving at 20 meters per second. So that's going to be my u. And say it gets up to a velocity of 50 meters per second, and it took it a time of 10 seconds to do that. So in any given situation, we really only need 3 of the 5 quantities to be known, and we can solve the other 2. And here's why. Because if you look back at the equations, each equation has only 4 variables within it, because the 5th one is missing. So you only need 3 to solve for the 4th one. So I'm going to list out my variables. Suvat, displacement is not known. Initial velocity is 20, final velocity is 50, and the time was 10 seconds. And let's say the question is asking us for the acceleration. So this means I don't need a displacement. And here's how you use the equations. You identify the variable that's not mentioned or not needed. In this case, it's displacement. And you go back to one of our 5 equations and look for the one that does not have displacement in it. And that would be, oops, sorry, this one didn't have displacement, not time. So it would be this one. This one has no s in it, and I don't need it, so I'm going to write down this equation on here, which is v is u plus at. And then I can rearrange this to find that acceleration is, of course, the change in velocity over time, which would be 50 minus 20 over 10, which gives me 3 meters per second squared. Right? So, sorry, that's not supposed to be there. And then once we get this, and if the next part of the question asks me to find the displacement, I can now use any equation that has an s in it, because I already have the 4 variables. So let's go back and look at which one has s, meaning I can use all my equations except for the first one, because the first one doesn't have displacement in it. So let's choose the simplest one, which is the second one. So I'm going to choose this equation right here. So let's go back here and plug it in. Displacement is half initial plus final times time, which is half 20 plus 50 times 10. That makes that a 5. Then I have 70 times 5, which is 350 meters. So that's how far the car traveled in 10 seconds when accelerating uniformly from 20 meters per second to 50 meters per second. Second, the car's velocity is increasing by 2/3 kilometers per hour, so that after 60 seconds it would have gone up by 40 kilometers per hour, and if I add that to the initial 60 kilometers per hour, I find that the car is now moving at 100 kilometers per hour. Now acceleration is generally considered a vector because, as we'll see in later videos, the direction does matter for acceleration. It could result in different consequences, which I won't go into